Hello, in today's video we'll introduce the basics of sequences and series. Let's get started. So we begin by introducing a sequence using our roster notation set A sub n, where A sub n refers to the general term of your sequence, where the subscripts 1, 2, 3, all the way to n, for example, are your term number. So term 1, A sub 1, term 2, A sub 2, term 3, A sub 3, all the way to your general nth term, A sub n. They're going to be following a certain pattern, and so we begin by talking about two ways that we can write out the pattern for a sequence. The first is explicitly. To write down the pattern explicitly means to write down an equation that describes any term called your nth term of the sequence by simply knowing what n is, what term number you have. For example, if we have A sub n equals 5n minus 3, that kind of reminds us of the equation written like a function, f of x equals 5x minus 3, right? It's kind of like a linear equation here in this case. But what we want to do to write the terms out for this explicitly defined sequence is just replace n with the different term numbers that we're interested in. So for example, A sub 1 would be the first term when n is replaced with 1. So for example, 5 times 1 minus 3. You've done this before with function notation, haven't you? Just replacing your variable with the appropriate input. So in this case, 5 minus 3 is 2, and 2 must be our first term. So if I was writing out this explicitly defined sequence, the first term would be a 2. What about the second term? We'll simply replace n with 2, because this is an explicitly defined sequence. It just depends on your term number. So putting in n as 2, you'd get 10 minus 3, which is 7. Which means the second term of this sequence is a 7. Next up, we'd go to our third term. Replacing n with 3, we'd get 5 times 3, which is 15, minus 3, and 15 minus 3 is just 12. Now you might notice a pattern. Each time, you're jumping up from the next term to the next term, by adding 5 to your previous term. Notice that's what we're doing here, adding 5 each time. What that would mean is that we have what we call a common difference. It's basically like the slope of a line, right? In this case, the slope of this linear equation, if you will, is 5, meaning that each time n goes up by 1, your term itself goes up by 5. So for our fourth term then, you can imagine that if you replaced n with 4, you'd get 20, and subtract 3, you'd get 17. Which makes sense, because if you add 5 to 12, you would get 17. So 17 would be your fourth term of this arithmetic sequence. So it turns out this particular type of situation, which we'll study in a future video, our next video, will be an arithmetic situation because we had a common difference, in this case, of 5 between consecutive terms. So with that in mind, let's describe how we could also write an equation of a sequence. But instead of using the explicit version, this time we use the recursive version. Okay, you probably won't like this one as much, but let's take a look. So how do I write an equation recursively? Well, the first thing is you would need to tell the reader, or the person reading your problem, you would need to tell them what was your first term. So they start off by giving you a first term. In this case, A sub 1 equals 2. So if you're trying to write out the terms of your sequence, try to show you down here. There you can see a little bit of it. Your first term is given to you as a 2. So that will always be provided, the first term. But then what they're going to do is give you a relationship between two consecutive terms. This is the part where students get a little confused. So here we go. What they're trying to do is tell you what to do to your prior term. So they're trying to say, take your prior term, which is right here, A sub n, take your prior term, multiply it by negative 3 in this case, and then add 1 to it. That will give you your next term. Okay, so what we mean here by A sub n plus 1, since n plus 1 is 1 bigger than n, that implies that we are talking about how to get from one term to the next. We take negative 3, we multiply it by the previous term, and add 1. So for example, we were given that the first term was 2 here. How would we get the second term? We would take negative 3 times the previous term, which would be the first term, and we would add 1 to it. But the first term was given to me as 2, wasn't it? So this would be negative 3 times 2, that's right, adding 1, which is negative 6 plus 1, which is negative 5. So our second term in this situation is a -5 for our sequence. What about the third term? Well, the recursive definition again tells you how to get to the next term from the prior one. So we would take -3 times our previous term, which in this case was the second term, and then we'd add 1. But that's -3 times the prior term of -5 and add 1, which is 15 plus 1 or 16. Now this situation compared to the last example above, it's not arithmetic, is it? Because we're not simply adding the same number each time to get to our next term. Instead, we have a more complicated formula or function, if you will, to get a new output from an old input. Go ahead and see if you can try the fourth term on your own. What would I need to do? Pause the video and check with me afterward. Okay, how did you do? Did you do -3 times the third term and then add 1 to it? And what was your third term? It was 16. So -3 times your positive 16, that's -48, plus 1. Did you get -47? That's what I got. Good job. And this sequence would continue forever that way. We usually write the 3 dots at the end. That's called an ellipse of dots. It means go on like that forever. Continue like that. So in this case, we've described 2 ways on this slide, 2 ways to write down a sequence formula that describes what's going on between consecutive terms of a sequence. We prefer, as you might have noticed, the explicit version. We prefer the explicit version, the first one that we did, and that's because as soon as you know the term number, whether it's the 10th term, the 5th term, or the 100th term, you can simply replace n with that number, the term number, and you will have that actual term. Okay, so it's very, very nice. It's like function notation. But the recursive formula is actually very helpful for students who are just getting used to sequences and they really don't know what the pattern is, but they can see what I did to the last term to get here. So the recursive is nice when you're starting out, but as you move forward, we'd like you to get more sophisticated and seek out an explicit formula. So let's continue with formulas and these definitions on our next slide. In example 1, we're asking you to come up with the first 4 terms of this sequence described below. Now, what type of sequence have I described? Is it explicit or recursive? I've given you a sub 1 equals -4, and I've told you that a sub n plus 1 equals -3 times a sub n plus 5. Would this be explicit or recursive? Good job, it's recursive. The reason I know it's recursive is because they've given me the first term and the relation between 2 consecutive terms. So again, take a moment, pause the video, see how you do, and then come back and check. Notice they gave us the first term, -4. So to get to the second term, what did you do? That's right, you took -3 times the previous term, which was my first term, 4, and you added 5. When you did that, you would get -3 times -4, which is 12, and 12 plus 5 was 17. So your next term there should have been 17 for term 2. Your first term was -4. Okay, well, what about your third term? What would your third term have been? Well, you would have again done -3 times your previous term, which was a sub 2, and add 5. Well, that would have been -3 times what was your previous term? Well, your second term was 17. Good job. And then add 5. So in this example, in example 1 here, we've gotten a situation where we did -3 times 17 and then we added 5. And what did you get as your result? That's right, -46. Now, what's happening in between these terms is we're switching from one sign to the next, right? We were negative, then we're positive, and then we're negative. We're going to talk in a few minutes about how you can write that explicitly, that sign change, when you go back and forth between a negative and a positive and switch on and off, okay? So there is a way to describe this explicitly, but right now we're just describing for you how to get from one term to the next recursively. And for that fourth term, when you worked it out the same way, -3 times your previous term, which was -46, and add 5, did you end up getting a result of 143 by plugging in that -46? I hope so. And that would have been your fourth term of the sequence. So one of the skills that you'll want to practice is the skill that we've been working on so far, where we give you the sequence defined recursively or explicitly, and you have to interpret what that's saying to get at least 4 terms, maybe 5. Okay, so make sure you do a lot of practice with that to understand what this is saying formulaically. Let's head over to another slide here, where we practice this time coming up with the term ourselves. So it says, can you write or can you describe the general term a sub n, where n starts at 1, n is greater than or equal to 1, for this sequence below? We start with the term -3, then we jump up to 6, then we go backwards to -9, and then we go back positively to +12. Now, some of you can see that what I mentioned a moment ago is happening here again, right? We're changing between negative and positive, negative and positive. So in a minute, we'll talk about the sign change and how we could write that explicitly. By the way, anytime they ask you for the general term, they're wanting it to be written explicitly, meaning in function notation, if you will, depending only on n, the term number. So let's see if we can do this by ignoring the sign change for a moment. So if I ignore the sign changes for a moment, how would I figure out, that's supposed to be a G, how would I figure out what's going on here? Oops, let me get my eraser so you can see that better. Ignoring your sign changes, how would I figure out what's going on here? There's the word changes. Well, what I would do is I would look at my term number. So I noticed that when n equals 1, the positive one without the sign would be 3. When n equals 2, I would have 6. When n equals 3, I have 9 as my term. And when my term number is the fourth term, n equals 4, I have the term 12. Do I see a pattern for my nth term currently? Between n, the term number, and 3, let's say, the term itself. Between n equals 2 and the term 6. Between n equals 3 and the term 9. Between n equals 4 and the term 12. Do you see a pattern? You can take your time and pause the video and come back. Well, yeah, each time we're really multiplying n by something. What are we multiplying the term number by? That's right, 3 times my term number. In other words, 3 times n. 3 times my term number is producing each term. So I could notice that this appears to be my pattern, right? So for example, for the fifth term, I would do 3 times 5, which is 15, right? Which makes sense, but we have to now incorporate the sign change. So let me come to the side here and give you a little trick for oscillating or alternating, if you prefer, signs. You're going to use this trick, by the way, in calculus all the time. Anytime you have oscillating signs and you like to describe the situation theoretically, explicitly, what you want to notice is that if you're switching from negative to positive, positive, etc., like that, back and forth, what's really happening is each time your term is getting multiplied by a negative number, namely -1. So what we would do in this case is we would use this idea, -1 to some power. But what power? Would I use the term number n itself, or would I make it like n plus 1 or n minus 1? Well, let's take a look at what happens here. If I use the term itself, the term number itself, I should say, n, then if, for example, for the first case here, would I start off with a positive or a -3? Well, if you put 1 in, you would have as your exponent -1 to the first power. Anytime you take a negative and you raise it to an odd power, won't that be negative? It would. So this would, in fact, begin with -3 here. So what I would recommend writing for my formula would be -1 to the n times 3n. That's one way to describe explicitly any term of this sequence. On the other hand, to make a little note here, if it had gone from positive to negative, and then positive to negative, and continued alternating or oscillating like that, instead of using -1 to the term number, I would have used -1 to either 1 above the term number or 1 below the term number. I prefer n plus 1, but you could have used -1 to the n minus 1. Both of them do the same thing, and you should check it out. For example, if I had used the n plus 1 or the n minus 1, what would have happened for my first term? Well, 1 plus 1 is 2, which is even. And if you take a negative to an even power, that's right, it's positive. So that would have made our first term a +3 instead of a -3. Similarly, if you had used n minus 1, replacing your n with 1 there, you'd have an exponent of 1 minus 1, which is 0. And anything, even -1, to the 0 power is just 1, meaning it stays positive. So that's really the distinction. Which of these situations do you have? Would you like to start with a negative and then switch to positive and keep going like that? In that case, -1 to the n. Are you starting with the positive and then switching to a negative? In that case, -1 to the n plus 1 or to the n minus 1 will do the trick. Okay, there are other ways to describe this sequence, but this is the easiest way to describe it explicitly. So definitely take some time and practice that skill before you go on in this video. Okay, the next topic of this video is how to express the sum, so adding up, of a sequence, adding up terms of a sequence, using a new notation for many of you called summation notation. Kind of rhymes. Now, the symbol that we're going to be using for summation notation, as you can see in the slide there in that white picture, you can see that that symbol is a capital Greek letter, which you may have seen before, whether if you're in a fraternity or sorority and use a lot of Greek there, or if you've ever used Microsoft Excel. You've seen this symbol before. Remember that the Greek Greek alphabet has uppercase and lowercase lettering system. I can't speak. Uppercase and lowercase letters. So for sigma, for example, if it's uppercase, this is the capital letter sigma. It is like our English letter S, right? Their lowercase sigma, by the way, looks like this, almost like an O with a little hat at the end. And that is what we normally use in statistics for our standard deviation of a population of data. But when we have the capital letter sigma in a math context, that means add up whatever comes after this, okay? So you can see in your picture on the right there on the slide that what we have when we see this symbol is an instruction. It's an operation. It says add up the terms of whatever is to the right of it, the terms of this sequence, and it tells you below that sigma where to start your term number. So start here where k is 1, and on top, whatever number you see, that's where we'll stop. So from this term number until this term number. Notice they're not saying from this term to this term, but rather the term number that you plug in. So we're going to first look at an example of how I could rewrite a summation using this notation. So let's look below at 2 plus 4 plus 6 plus 8, and then notice that ellipse of dots again, dot, 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 means continue like this until you stop at the term 102. So if I wanted to use summation notation to describe this operation of adding up 2 plus 4 plus 6 plus 8 all the way to 102, what I would do is I would begin by using that Greek capital letter sigma, which means add up anything that comes to the right of this. Now usually, just so you can get this correct in your textbook as well as on your online homework, usually when you put your sequence next, you want to put it in parentheses to make sure that the reader knows that everything that comes after it, that term, each iteration is being added together. So that's going to be your sequence, if you will. So we're going to come up with our sequence explicitly, which is what we just practiced in our previous examples. But we need to tell the reader where to start. So we're always going to tell the reader to start at a certain value, like n equals or I equals or k equals. You can pick whatever variable you like, but you have to be consistent to use the same letter in your problem, until a certain number here, wherever you stop. So you tell it where to start, and you tell it where to stop. So let's see how this would look in our situation. We've done one like this already, where we said, in this case, 2 is our first term, so that's n equals 1. 4 is our second term, that's n equals 2. 6 is our third term when n equals 3. 8 is our fourth term when n equals 4. And you might be wondering, well, what term number is this? When I get the output of 102, what term number would produce that output? Well, you might already see the pattern, and if you do, excellent. This time, we are adding 2 to the prior term. So recursively, you'd start at 2, and you'd add 2 to your previous term to get to your next term. In other words, it looks like this sequence is what? Well, if you start with noticing the n, how do you get from that n to its term? What do you multiply n by? That's right, you're multiplying your n's by 2, aren't you? Because 2 times 1 is 2, and 2 times 2 is 4, and 2 times 3 is 6, etc. 2 times 4 is 8. So now that you know the sequence pattern that's going to go into your actual sigma notation, summation notation, could you find the stopping point? Because at this point, you can now write sigma, you can rewrite this as sigma. You know the sequence, it's just 2n. Usually we use parentheses to tell the reader that whole thing is our sequence that we're iterating. And now we need to tell the reader where to start and where to stop, or your computer if you're programming this. You would start somewhere and you'd stop somewhere. Now, notice what's tempting is to say start at 2 and stop at 102, but that would be wrong because we're supposed to tell it the term number. So we're starting when n equals 1, and what term number am I stopping at? Well, you might see it. It's 51, but here's how you could get 51. You take your actual sequence and you set it equal to this last term, 102, and then you solve for n. Dividing both sides by 2, you'd get 51, wouldn't you? So n is, in fact, 51. That's the 51st term that we're going to be stopping at. You tell the reader that's where you want to start and stop. So now using this notation, what you'll be able to do, you'll be empowered to do, is if you click on any of these video links on your notes, the TI-83 tutorial, the TI-84 tutorial, or the Symbol Lab solution, you would be able to input this notation into any of those softwares, and it would immediately add up those terms for you, rather than taking a calculator or doing this in your head, 2 plus 4 plus 6 plus 8, until you get to 102. This is a much more sophisticated way of having writing the program basically for your technology to finish. Now, the good news is, in a future video for 9.2, 9.3 in this textbook anyway, but in a future video, when we talk about sums of sequences and sums of series, we'll be able to do this one by hand as well. We won't have to depend on technology. But for right now, as you go through these problems to practice this section, what I want you to really focus on is, how would I rewrite this summation, this sum, as a sigma notation problem? Basically as an input instructions for technology. That's what I want you to focus on, getting used to the notation, okay? So let's take a look at our next example of doing just that. Example 3 says, please write in summation notation 1 plus 2 over 6, but instead of writing 6, they've written 2 times 3. Interesting. Plus 2 over 12, but they've written 3 times 4. Plus 2 over 20, or 4 times 5, all the way until you get to 2 over 90, where 9 times 10 is how we're writing 90. Now you might be wondering, why are they writing it this way? We don't normally do that. Well, they're trying to give you a hint. They're trying to show you what the pattern is. And what I usually like to tell students, as you're figuring out what the sequence pattern is, I usually like to tell them to, if you see that there's a pattern maybe for most of the terms, but there's one that's kind of different, ignore the anomaly, ignore the one that looks different, and then we'll come back at the end with our suggested or hypothesized pattern, and we'll see if it applies. So let's take a look at what's happening to these terms after our first one, because our first one looks very different. So what I notice here for my sequence is that I have a 2 each time. And at any point, if you'd like to pause it and try it yourself, feel free. I don't want to rush you. But we have a 2 on top here, okay? But on the bottom, for the second term here, this is when n is 2, when n is 3, when n is 4, and we don't know what n is here, but you might see it already, okay? And here, when n is 1, we had 1. But we see that 2 is always on top, at least for these terms. And on the bottom, we have 2 times 3 when n is 2, so that's matching the term number. We have 3 times 4 when n is 3. We have 4 times 5 when n is 4. So you might have an idea now that maybe this last term is when n is, that's right, 9. Can you go ahead and write down what you think is the pattern, and then pause and come back to me, see how you did? Did you get n, and then that's being multiplied by 1 more than n plus 1? If you did, great job. Some of you may have decided to really show off and distribute, and so maybe you wrote 2 over n squared plus n. If you did, excellent job. They say the same thing. Okay. Now, what you want to do is test, does this actually work for my first term, right? Because my first term looked a little different. But if you checked, let's do a little check. Did it work for my first term? Well, a sub 1, the first term, would have been 2 over 1 times 1 plus 1, wouldn't it? Which is really 2 over 1 times 2. But notice what happens. Isn't that going to just be a 1 because 2 over 2 is 1? It is. And so yes, it did work for the first term. And so that's why we usually go to the ones where we can see that there might be a pattern, focus on them to find the pattern, and then fit that pattern to the one that looked different and see if it actually works. Okay, so now we know the name of the sequence. This is the sequence pattern, right, for the nth term. We can get any term if we know its term number n. So how do we write this in summation notation now? Sigma or summation notation, because it's a sum, we're adding these terms up. Well, that's right. We would say this would equal capital Greek letter sigma, take our sequence pattern and input it usually in parentheses, so 2 over n times n plus 1, or if you prefer n squared plus n. And then we tell the reader, or the computer technology, where to start and where to stop the iteration. So starting when n is what term number and stopping where? That's right, from n equals 1 until n equals 9. So the first 9 terms of this sequence are being added together. And we'll do a lot more with that in our future videos. Okay. Now on our last slide, so feel free to practice that skill as well, but on our last slide what I'd like to show you are a few different patterns that might be helpful to you. Okay? So when you see summation notation like we have in example 4, sometimes we can use a shortcut to get those sums. Other times we'll just have to write them out. The first shortcut that we see in the white box on the left here above my head, we see a situation where inside of your argument here, your sequence if you will, is a constant. And if that's a constant like the number 5, we're really saying add that term over and over again, starting at the first term and stopping when k equals that n. Okay? So for example, we have that in part B. So in part B here of our example it says, can you add up the sequence 12, starting when I equals 1 and stopping at I equals 4? What is that saying? Well, technically it's saying 12 starting at the first term, so when I equals 1, plus, because it's summation, that means add, 12 again, because that's the second term when I equals 2, plus 12 again, I'm being very dramatic, writing them all out, when I equals 3, and plus 12 one more time when I equals 4. You might have wondered, why did we even need I? I didn't see I in the sequence equation. That's true, but that's your term number, so you need to make sure that's there. So what ended up happening? Well, we had 4 copies of 12. So couldn't I have just done 4 times 12, or 48? And that's what that shortcut is suggesting. You might not have seen it before, but here's what it's saying. If I have a constant here, and I'm starting at 1 and ending at some number, I could simply multiply the upper limit here times my sequence constant, 4 times 12, and I'll get my answer a little bit faster than writing it out. So if you like that, feel free to use that. The second and third and fourth shortcuts there, they work exactly as they look. So if you take a peek at them real quick before we call this video done, if you have a coefficient of your sequence, like we had in the last one where it was 2n, it turns out that you could factor out that 2. And that makes sense, right? We had 2 plus 4 plus 6 plus 8 all the way to 102. They're all divisible by that number 2. So if we factored it out in front, that would work the same as multiplying 2 times that sum. And that's what we're seeing here. We can always kick out our constant into the front. Now that's not happening here, but if you had a number like a 2k cubed, for example 4a, you could have put that 2 in front. That's what we're saying there. Okay, so that shortcut can save you time if you see it. If you don't see it, you'll just do it the long way. The last 2 examples there, sorry, not examples, but points, 3 and 4, they're talking about the fact that if you have a very complicated sequence, like k squared plus 3k plus 7, you can actually separate it into 3 different sequences. So every time you see a sum in your sequence, you can separate it into a sum of 2 sequences. Anytime you see a difference in your sequence, you can simply separate it into a difference of 2 sequences. And that can save you time as well. But in example 4a, we really don't have any tricks there. So let's take a look at what it's asking. It says we have the sum of the sequence k to the 3rd power, and we would like you to start iterating at k equals 0 and stop the iteration when k is 4. So you're inputting this to technology and it can respond very nicely. But as a human, do you understand what this is saying? Okay. The technology does, but do you? All right, so let's take a look. Well, you would start with k being 0. So 0 to the 3rd power. That's when k equals 0. Now this one's a little tricky because we're used to starting at 1, not 0, aren't we? Take a look at the next term. It would be when k equals 1. So we'd have 1 to the 3rd power. What about the next one? When k equals 2, what would you have? That's right, 2 to the 3rd power. And finally, the last 2 terms would be 3 to the 3rd power and then 4 to the 3rd power. So what would our answer be? Go ahead and take a moment. You can pause the video and check it yourself. Did you get 0 plus 1 plus 8 plus 27 plus 64 for a resounding answer of, that's right, 100? And again, your technology could have done that had you inputted it correctly into your calculator or your computer. But what we'd like for you to be able to develop in this section as you're working through some problems on your own is we would like for you to be able to understand what summation notation is saying. That will be very vital as you go into calculus. One of the first things you'll do in Calculus 1 will be to rewrite multiplication of length times width, length times width, length times width for rectangles to get area under a curve using summation notation. So you will have to be very skilled at reading and writing in summation notation, not only for this class, but in many classes to come. All right, well, I believe that concludes this video. So before I see you next time, make sure you practice, because as we say all the time, math is not a spectator sport. I'll see you next time.